just gonna switch to the straight slideshow. You're good. Sorry, just his face.
Wait.
Can they hear us? You should do the intro. I don't know.
No,
I don't know what's
just yeah, air.
Okay. All right, welcome everybody to the 2026 competition year CSU PDR. We'll go ahead and get started. So our itinerary today is, first we're going to start with mission overview, requirements recap, systems architecture overview, which includes the mechanical, electrical, and computer sub-teams that we've split down our team into. And then we have our integration overview, our preliminary risks, our verification plan, and our planning, which includes scheduling, budget, and then we have questions for afterwards. So the mission of NASA Lunabotics is to design, build, and test a prototype lunar excavation rover at NASA Kennedy Space Center and at UCF to deposit regolith in a berm construction zone from the excavation zone of the berm area. Key berm functions include blast protection, radiation shielding, thermal management, and environmental safety for facilities. This is our third year participating. We came into the competition in 2024, and we competed in the 2025 competition as well. The Artemis arena layout is slightly different from last year. They increased the distance that the robot has to maneuver through the maneuvering zone to get from the starting zone to the deposition zone. Requirements: we have to excavate in the designated zone, and we have to traverse obstacles, which include 30 to 40 centimeter boulders and craters that are 40 to 50 centimeters across. We have to construct the berm precisely. Anything outside the designated berm zone, even if it is in the deposition zone, does not count. And we cannot anchor the robot to the regolith in any way or ram the walls. Scoring matrix, one part of that is our BCP score, which basically divides the robot's mass under the regolith deposited, and then the BCP energy score, which divides the deposited regolith with the energy used. We get penalties for obstacle contact, dust issues, and communication failures.
So these are requirements for the competition for physical design requirements. So the robot has to be under 150 centimeters fully extended, 75 meters wide, 150 centimeters in length, under 75 centimeters wide, and then under 250 centimeters when it's fully deployed, if we have parts that extend. The total mass has to be under 80 kilograms. We have to have 4 designated lifting points for every 20 kilograms that the robot weighs. And then there's other requirements such as the E-stop, which is a physical kill switch. We're going to have power logging on board so that the power usages can be monitored externally. And then other things like battery, safe battery charging, inspection if the robot is dropped, and then making sure that electronics are sealed are other preliminary requirements. Risks, again, these are just generalized for the competition, so we have to think about dust and how that can contaminate different areas of the robot. Autonomy and navigation failures, if the robot somehow loses its navigational features and has the ability to hit a wall or something that it's not supposed to, we have to make sure we have safety precautions in for that. Performance shortfalls, not being able to actually meet the objective of the competition by moving regolith to a certain area will have to be accounted for with autonomy scoring at the bare minimum. And then, of course, there's generalized programmatic things like delays with parts and having to redesign certain things. And then integrating all the sub-teams together with all the safety features is another thing that we have to take into consideration. This is our Gantt chart as of right now. It just has all the sub-teams divided. And we have some, again, overall club programmatic type goals set here too for things like the deliverables such as the PDR and then later the CDR. So we have three primary design sub-teams. So we have mechanical, electrical, and computer science. Mechanical works on the frame of the robot. Electrical works on various motors and other components that allow for movement. And the computer science works on autonomy, interfacing with those electrical components. And I will hand it over to Jared for mechanical.
All right, so we'll start us off for the mechanical sub-team. Firstly, we're going to look at several different mechanical locomotion methods. Last year, we had some success with using a tracked system, and we can still go back to that if we need to. It weighs about 55 kilograms. The biggest problem is that the chain needs to be dusted between runs, and it needs to be shielded this year if we decide to use it from regolith, which caused us last year to bind up the tracks and shear the axles. So if we do use tracks again, we're going to have to look at that and weigh those pros and cons against our next locomotion method. We can raise and lower the tensioning bracket, which you can see there in the middle of the tracks poking up. That adds tension to the tracks. It keeps them from loosening and basically dipping down and contacting the top of the motors and gearboxes and wearing those. It has 8 times drive sprockets, 4 NEMA 34 brushless DC motors to drive those, and it runs through a 1 to 30 reduction gearbox. Next design, which we've been working on this year and is our favorite to use, is wheels. Altogether, this system weighs about 33 kilograms, which is a saving of 22 from last year, so about 40 pounds, 45 pounds. That's not right. So this year, it'll be powered by 6 times NEMA 23 brushless DC motors using a planetary reduction gearbox. Some of the info on here isn't exactly correct. That's what we're working on right now, and so we'll move on to our digging system options. So our first digging system design, that's not a bulldozer. That is the front loader design that we have been working on. It is not entirely done in CAD yet, so you don't have a picture there, but we are working on it, and it is our favorite this year because it performed very well at competition last year. We're going to use 3 to 4 Figurelli heavy-duty actuators to move that blade up and down and to rotate it once in the air. It's probably going to be made out of carbon fiber for the flat portions, reinforced with steel on the edges, just to reduce weight. Next option, which we are carrying over from last year's unchosen designs, is a bucket chain. It's about 20 kilograms without the frame, and it must be shielded from regolith. Like we said with the track system earlier, if regolith gets into the chains, it will jam them up and we will have axles shear. For adjustments, you can raise and lower the tracked bucket chain system, and you can dump the bed, which you see there right above the box labeled electrical box, and that allows us to move forward while continuously digging and then deposit regolith out the back of the robot. And I'll hand it off to our electrical team.
You want to start?
Yeah.
No.
So I'm Adam Carbone. This is Kevin,
Kevin Bulldozer.
and we are the electrical and leads. So this is a generalized system diagram for the electrical sub-team for an idealized system. So we have, like Jared was saying, for a 6-motor system, we have 6 BLDC motors that get power from a 24-volt battery or some higher voltage battery. And then again, for a bulldozer configuration, we have actuators to move the blade up and down. And then there's various other components like low voltage power converters, microcontrollers that actually drive the motors, which in this case would be onboard motor controllers instead of just external to the other hardware like a primary controller. And then we have a low voltage battery to keep the high voltage and low voltage systems isolated. So again, this is just going more over that. There's 24-volt battery, kill switch in between that, and then there's a power monitor in between those two so that we can always read power in between runs. And then, like I said, the primary other components are there's a master computer, there's microcontrollers on board to drive motors. There will be some sort of GPU, whether that's just a Nano or some other device. We are talking about Mac Minis on board, and then there will be 4 cameras for triangulation and navigation, and then Wi-Fi for telemetry. This is a design concept for a BLDC motor driver. We wanted to look into doing custom hardware versus just buying hardware to drive our motors. That way we have more control over data flow, so we can monitor our power, and also it's an accomplishment to say that we've designed our own hardware. So this is a sort of high-level diagram of the components that we need for a Texas Instrument driver chip. So looking at off-the-shelf drivers, they run you about $75 per one. We need 6 of them. They're pre-built modules, so they have heat sinks built in already. They already have predefined documentation. But besides that, you're kind of stuck with the modes that they give you by default on the controller itself. And then this is a design that the electrical subteam has been working on. On the left, you'll see a schematic in Altium Designer, which is a BLDC motor driver using I think it's a Texas Instrument driver. It drives 6 FETs. And then on the right, there is a PCB layout for that exact design, which is almost ready for I guess, pre-production run for prototyping, for prototyping purposes. But this is a design that we're working on. Again, the benefits of this is it's cheaper. We don't have the elements like the heatsink on board. We can obviously add stuff externally, so I would assume that with other components they would get closer to the off-the-shelf price, but again, it's custom hardware. We get to control it from the design all the way to how data flows, so it's better for us to understand how our own drivers work, do it a little bit cheaper, and it makes it a lot easier to integrate into the other subsystems. And then here is just a BOM that shows the breakdown of costs.
All right, yeah, so I'll talk a little bit about our design concepts regarding the electrical box enclosure. We're looking at a couple different options right now. Our big toss-up is between plastic and metal, specifically aluminum. Some things about plastic, it's a lot more lightweight. You'd have to go with pretty thin sheet metal for a metallic kind of enclosure to match what plastic can give you, and it'd be mounted using threaded inserts, probably just heated inserts that you can push into the plastic that you can then use for mounting to the chassis. And the other benefit of plastic is that it has minimal interference with the Wi-Fi signals which are being sent to and from the robot, meaning you can mount the antenna inside the box and not have to worry about sealing it in some kind of protrusion or extension that would have to run outside the box. As far as aluminum goes, one of the big reasons we're looking at using metal is its potential to be used as a heat sink, right? With the custom motor drivers being placed inside the box, that's a lot of heat that needs dissipated. Our previous designs, the controllers were integrated into the motors and they were mounted on the back, and they were already kind of in free air, I guess. So we didn't really have to worry about dissipating all that, but given our new design, we do. It'd be mounted using brackets, not too dissimilar to how you'd mount the plastic one, but would require a bit more work. And then the Wi-Fi antenna would need to be mounted on a pass-through and then using some kind of cable extension to be used to go from the antenna to the router. Just a couple things to consider, but we're at the end of the presentation, we're open to some suggestions or input on which design is better, in your guys' opinion, some pros, some cons, so I look forward to hearing from you later. All right, and then here's a preliminary power budget. We've got everything included from our BLDC motors, our controllers, our actuators. This is more so for us to gauge scoring, right? So the BCP for energy is your volume of regolith per minute divided by your energy. So this is kind of giving us a baseline of what we're shooting for in terms of that score, right? So 500 watts over the course of a half-hour run, so 250 watt hours. Did you say that's about like what we're shooting for?
Mm-hmm.
So
the peak isn't accurate estimate, as this is assuming that we're running most of the hardware under load, and most of the time the robot will not be running all 6 motors and all 4 or 3 actuators under load. So those are still things that we'll have to consider when we do a more accurate power budget, if we want to get a more accurate peak power draw, but the average power is probably a more fair estimate in this lower stage.
Right. There are, especially given the control that we have over the design and implementation of the motor drivers and controllers, it's very unlikely that we'd ever see anything close to 86 amps. I mean, you know, if you figure you run your 4-wheel motors at full torque, that's already pushing like 84 of those amps. It's, again, very unlikely that you'd ever see anything close to that in practice, but it's up there for, you know, just for the sake of being transparent.
Yeah. Do you see it? There it is.
You want to go
Yeah.
talk about this?
So this is looking at different types of interfaces for communication between components on board. So the first thing that we were looking at was CAN bus. Well, actually, I will start with I2C. The first thing we looked at technically was I2C. We were just weighing the pros and the cons of doing that versus a different type of communication. So I2C requires pull-up resistors over long distances. It's single-end communication. You have a data line and a clock line. And again, it's not, you can use it for longer distance communication, but you have to make sure that the lines are run pretty robust, and you don't want there to be any high frequency noise. For CAN bus, there's differential signaling, so you have a high line and a low line. Again, we can have a transceiver that's sort of a central hub in the robot, and it can receive all the communication from different devices, and then transmit I guess the response back based off of whatever the main computer is telling those devices to do. Everything has sort of IDs. You can send multiple messages at once over that type of interface. So it's a little bit more robust, a little bit more industrial. And then again, you can span CAN buses over pretty long distances, especially if you're using some sort of TTL transceiver. If you need to run super long lines. But again, our robot's not going to be more than 1.5 meters, so we won't even have to worry about anything like that. And then, yeah, that's pretty much it. Based off of the comparison, we're probably going to go with CAN bus just because there's already PCB components that allow us to do add a transceiver to our motor controller, so it just makes the integration a little bit easier.
Right, as Adam was saying, you can get away with longer distances for CAN bus. Not that I think we're going to be anywhere near, the upper limit of that. But I think off the top of my head, one rule of thumb I saw was max 40 centimeter distance for I2C. And while you can definitely get longer than that, it requires a lot of tweaking and a lot of making sure your line capacitance is, all accounted for. And it requires a lot of math and a lot of testing. The benefit over CAN bus, at least in my opinion, is just because you have your differential pair, any noise that one line sees is going to be reflected in the other one, and it's just a lot more robust. And when you're running 6, basically big electromagnets around all of your signals, I think it's a fair choice to want to pick that over I2C. But again, if anybody has any opposition to that, we can talk about it at the end of the presentation.
I want to actually point out that on our motor controller design, which is currently in early prototype phase, that the CAN lines are run here, and we try to keep them away from all the high power components, so that there's minimal amount of EMI around all the communication stuff. So they're on as far away as we can get them from the high power side of the board. So that is communication, and then.
Yes, and I am back up here to talk to you guys about connectors. So the connectors we've chosen this year, just like last year, are the Molex MX150L connectors. My favorite. They're IP67 rated, so rated against both water and dust ingress, which is very important in a dusty environment. It's kind of hard to find connectors that have that dust ingress rating. A lot of companies kind of just don't care about it, but these ones are rated up to 40 amps per circuit, so maybe not for the whole power distribution, but for power to each individual motor or motor controller, these are definitely a viable option, but they're also very viable for the signaling between the motors. Any connection that has to be made outside of the electrical box or going into the electrical box, these are a great candidate. Something that we have all of the tooling for already. If you know anything about crimpers, they can get very expensive very quickly. So having that material and those tools handy is definitely a big plus. Yeah, sealed for harsh environments. They lock and they don't come undone. You have to, actually manipulate the lever to be able to get it to come out. So there's no just it popping out on accident. So there's wire to board, wire to wire, and pass-through options. Like I mentioned earlier, they make connectors in this series which can be sealed against using like a rubber grommet, the outside of your enclosure. So really no opportunity for dust ingress there. And then for anything that would need higher power, we can look at other options. I know Anderson makes a lot of high power connectors, same thing with Amphenol. Something that maybe we aren't worried too much about dust ingress because we aren't worried so much. Like when you talk about higher power connectors like that, a lot of them aren't sealed, but they're sealed between the two sides, right? There's a wall, there's an insulating wall, so you're not really looking at any possibilities of shorts. And when you're talking about power, you're not really worried about signal integrity either. So that's something we can look at for like your battery connections, your battery to power distribution board connections, things like that. So. That's a CDR thing, I think.
And then the final thing that we have for the electrical sub-team here is risk management. It's building off of the original SRR table that we had. So it's just going over different metrics that we're trying to cover and think about while we design. So connector reliability, thinking about mitigating dust buildup, power surges, again, our motor controllers, things like that will have built-in current and voltage protection. So we're covering those bases as we go through different aspects of the design. Battery overdraw or fault, which again we have sensors on board. Motor stall, EMI, which will be part of our design testing and prototyping, and then of course the e-stop, which this year we have our physical e-stop, and then we're also planning on including a dedicated software e-stop so that we can send a single kill command to stop any operations on the robot. And that's pretty much it for electrical. And with that, we have software. All right, so this is a basic a software diagram, just a mini substructure for how we think we're going to lay this out. So as you can see, we have a bunch of April tags on the left there in the green, and then we have a 3D camera. So we're hoping that we can send a bunch of visual data to some sort of module that interprets like the graphical data. And then that will go to a bunch of other things for localization, for detecting objects. And then we'll have a state machine depending on what zone we're in so that we can figure out, so that the robot understands what area it's in and what it needs to do next. We're planning on including machine learning in this project, so we're going to use TensorFlow to build models that will actually be switched with the state machine, so that when it's in a certain zone, it performs one operation. When it completes the operation successfully, it moves to the next state and it navigates back to where it needs to go. And then that's all controlled externally, again, through CAN or I2C to some sort of microcontroller, which again will be on board our motor drivers, and then that will control, the drive motors and the actuator motors. So this is just going over that, I guess in a literal interpretation. But again, we have April tags, a 3D camera. We'll probably have more cameras than just the 3D camera in the front, in order to do our our triangulation with the April tags, and then the 3D camera will be specifically for object avoidance. There'll be a processing layer for localization, perception, and zone awareness. The control layer will have a state machine again with different modes of machine learning using TensorFlow. And then we have the actual physical layer that is controlled by those states. Hardware, so we were debating different types of computational devices. There's multiple routes we could take here. First and most obvious is a Raspberry Pi. The Raspberry Pi would work for most of our general, I guess, system sort of control, so like sending signals to hardware, such as motor controllers. But when we start getting into the graphical processing, a Pi won't cut it. So then we have other alternatives such as a Jetson Nano, so it has onboard GPU, so it allows us to do a little bit more with vision processing. And then the other method, which I think we're steering towards, assuming that we have a budget for, is putting on board a Mac Mini with some sort of USB CAN interface, so that we can perform very fast, real-time machine learning. And again, depending on how we decide to train this machine learning model, visual processing may not be as intensive as we expect, but if we end up doing any sort of machine learning with the 3D camera and actual visual interpretation, then a Mac Mini would be the way to go.
Yeah, and also it's just very user friendly and kind of a familiar development experience, which is just kind of a time saver for us, and we know that for a fact that it'll have any kind of computational power that we need it to. So that's another reason we're considering that.
And then, like I said, peripherals. So with whatever primary computer we have, we'll have onboard microcontrollers. Now, we might be doing away with having Raspberry Pi Picos on board, since most of our custom hardware will have microcontrollers on board anyways. So it'll just be some sort of CAN interface going directly to all the peripherals, besides things that are USB, like the cameras, which will just go straight to the computer. And then we'll have other sensors, but I know we'll have current sensors on board as of right now, and then we have the integrated sensors in the motor controllers already for, there's tons of fault detection for over current, over voltage. We can change a bunch of different parameters. And then LiDAR is another thing that we can consider. Again, a lot of these are interchangeable, so it'll be up to how we want to integrate this into the final subsystem, but those are all different options and what we've considered so far. And then we have, we're also debating talking about integrating an IMU on board. So just some sort of accelerometers that we can compare our triangulated position versus what we're estimating. We didn't have this last year. Last year was purely just we just purely had localization based off of our movement. So like being able to compare a metric of where we think we are versus where it appears that we are is very useful, especially in situations where you might lose I guess visuals, such as the pillar that is in the middle of the Artemis arena. So there's a lot of use cases where we could actually use some sort of other, I guess, external telemetry than just how we think we're moving based off of our April tag localization.
Yeah, and last year we had a lot more freedom with where we could put April tags, which kind of guaranteed that we would be able to triangulate, because you could kind of throw them anywhere on the walls. But now you can only put them in the starting zone, so there's no guarantee that we will even necessarily be able to triangulate. And so we need some way to know where we are, and this was kind of one of the first solutions that came to mind.
And if anyone's wondering, these specs were straight off of the data sheet for this IMU. So don't read it too hard, but just don't read it too hard. There was definitely not integrated graphics on that. So next, this is going through the operation. for software. So, of course, we're going to have a controller. That will probably be some sort of custom-built software on board a laptop. And that laptop will be connected to the network switch provided by the competition. And that, in turn, will connect to the router that talks to the robot. We haven't actually discussed if we're going to use onboard Wi-Fi or some sort of external receiver or I guess transceiver for the Wi-Fi. That is something we have to consider, but regardless, that is the general structure for wireless data between our, I guess, control unit and then the robot itself. There's point deductions for using arena cameras, and then there's also point deductions for using too much data, streaming too much data. So there's going to be a balance between minimizing our data and also not using the provided visuals that they give us. Why does this keep? Am I doing? So we, of course, to be able to select a type of machine learning that we want to use for this, we had to experiment a little bit in the early stages. So this here is a little web app that we created that allows us to train a model in 2D to navigate around a fake environment. So there's a rover here, it has a bound box. There's a little digging area here. It can pick up these little orbs and it can move them over to this deposit zone. Every black dot you see is a crater, and the gray ones are rocks. And they can be between, the rocks can be between 30 and 40 centimeters. The craters can be between 40 and 50 centimeters. And in this simulation environment, they randomly spawn every time the robot collides with something or fails its objective. So the robot continuously learns how to navigate its environment and obtain the most points in the context of the competition just by doing better each time. So this is a PPO model. It's just adding data to a model and it collects data, gets better at doing better, and then that's it. There's other models that we'll have to explore too. There's things like Q-learning that allow us to actually modify weights while training. So instead of just feeding it a bunch of good and bad data, we're saying we actually train it in a way where it recognizes it did something bad and it changes its bad behavior by getting rid of the thing that made it perform the incorrect behavior. So there's a lot of different conceptual things we can do, but this is the first thing that we did, tried. There were some issues with this. There was latency because this is a web app, so we used a WebSocket to train it with Python TensorFlow. There was latency issues, so we got to a point where it sort of, I guess the training success kind of converged because it kept oscillating due to the latency, and we had to switch methods. So I'll hand it over to David for the next part.
Yeah, so pretty much, as you said, we ran into latency issues with the web app. So this is a local version, just written in Python. It pretty much has, the goal is to have all of the same features. It's mostly implemented so far. I tried to make it look as similar as possible and behave as similar as possible. And so there's still a few things that need to be implemented, digging, and also the layout of the obstacles. And as we're doing this, we're kind of trying to make it build in features that are as realistic as possible. So previously we were just able to turn and move, but as I implemented this, I implemented kind of a tank drive sort of thing like our robot's most likely going to do. So it pretty much turns all the wheels on one side and it just applies a torque. And then also we talked about, see if you can see, can you go to your previous slide? Sorry, or not. Oops. So yeah, originally this frustum here could just pick up any particles or obstacles that were in its path, even if they were behind others, because
it's just a viewing
area. Just an area, yeah. So next on our to-do list to implement is to kind of shoot out beams that are like almost how a LiDAR works.
So yeah, it'll be like a array-based frustum, which allows you to only see objects in front of you and not objects that are covering other objects in your view.
Yeah, and so we're just kind of trying to build this to be more and more realistic. So then, when we train our AI model, it will, hopefully be able to just be placed into an arena much more without too many modifications.
And there's multiple considerations with that. You could feed it, we could interpret the 3D data that we have ourselves and feed it 2D positional data and train it exactly as we're showing you right now. Whereas there's the alternative is that we could actually just feed an AI all the 3D data and let it learn on its own. So that, again, that would be, you know, more computationally intensive, but at this point we're just testing different methods to figure out what is the best for us as a design team and what's the most practical. So yeah, again, this is just going in sort of into what we just talked about. It's just the stated version of it, but we're using TensorFlow, Python TensorFlow. It's a very popular library for machine learning. My environment and his, they can support up to, the robots are supposed to be able to navigate around 5 obstacles. We have diggable objects, which will probably change to some sort of area digging. We don't know how it's going to work yet, but just to make it a little bit more realistic to how it'll actually be. And then, yeah, we're training it to on the same parameters as of the competition, which is that we want we want it to achieve the best mass to energy ratio. So it's how do you move the most amount of regolith with the least amount of energy, least amount of distance, with the least amount of movement, pretty much. And yeah, so we're using stable baseline 3, which is a TensorFlow default for training models like PPO, and then there's other parameters like how long does it have to get to its final destination and such, but we're still in early testing stages, so that's a little bit on that. And then the final thing for software is risk management. So just like electrical, we have to consider software integration failures. So if we for some reason can't get the machine learning working, then we want to have at least some sort of manual control ready. Again, that sort of goes with autonomy logic. If we can't get every stage working, even if it's partial autonomy, we want to be able to make sure that we can accommodate that when we're running it live. We have to account for communication latency. There is a built-in delay because they're simulating lunar communication from Earth. We have to consider data loss because it's always possible running high-power electronics that we could have data loss. We want to make sure that everything is communicating properly. And then this year we want to implement a lot of like logging and processing. So just collecting data and making sure that things line up and documenting it rather than just running blindly and just from interpretations of, oh, it's working or it's not working. And that's it for our entire PDR. Any questions?
Yeah, we want to open up, take this time to open the floor up to you guys to say what feedback, what questions, anything about what was discussed. I mean, on the electrical side, I know we were interested in any feedback on like the enclosure or Pat?
For the electrical box, in choosing metal one, couldn't the robotics itself go up a static charge just due to particle size of the regolith and just the static buildup of charge?
You're saying that for the electrical enclosure, if it was metal, it may just have the particles start sticking to it?
Or just because it just builds up, or if it gets picked up due to particle size, it could just build a static charge.
Yeah, that is something to consider. I don't know that it happens on metal as much as it does plastic. If anything, I'd say plastic would probably be more prone to that. That being said, on the stationary parts of the robot specifically, like your enclosures, anywhere that's really not like a joint or have any bearings or anything like that, I don't know that we're worried about it too much, but that is definitely something to consider. But you're right, the electrical box being conductive may present some issues in terms of static electricity. But
I might have something to add to
Could
that.
that also cause grounding issues perhaps? Since you're using it as a heat sink, you will be connecting electronics to it.
Yes, yes and no, I'd say. So how we'd end up sinking the heat, ideally, would be the FETs would have to be placed on the bottom of the board. And then we would just press the FETs, the tops of the FETs to the bottom of the board. Just kind of like how you'd attach a heat sink to the top of a FET otherwise, or any other high power component like a CPU, if any of you guys are into building your own computers and stuff.
So we don't have to, the electronics don't have to be grounded, but we also don't know if that would be beneficial to,
Yeah,
to our
actually,
electrical design.
that's another thing. If anybody here has any input on
The chassis.
grounding schemes to like the chassis of a robot, that's another thing.
It should already
Somebody
be
has some feedback.
grounded. The entire frame's made out of carbon fiber and aluminum,
To the box itself.
Okay, well,
and it's gotten spokes down to the wheels.
Does that answer your question though? Okay. Anyone else?
Yeah,
Yep.
could you tell me more about how you plan on training the AI model?
Yeah, anything specific or just in general?
Like, I know AI models, they require a lot of data to train, and I'm just wondering how you're gonna feed it good data.
So, like, we're, there,
Transition from 2D to 3D.
yeah, so like there's multiple avenues we could take. We were training this purely off of just trial and error. So we're not even giving it data to start with. It's just figuring out based off our reward and penalty system how to get around objects. So if I run into a rock, minus 50 points. And then every time it doesn't run into a rock and it gets, further and further it progresses, it might pick up, some sort of dirt or regolith, and then it gets a reward for that. So as it progresses from its learning, it'll eventually reach higher and higher checkpoints. So you could train it that way. We could also go the route where we train it by hand, where we actually drive the rover around ourselves in a few simulations, and then we feed it that data, and it learns how to drive in a similar behavior to how we drive. And then once it you get it kick-started, it can start training itself because it has enough basic data that it can self-sustain its own training. And that's just all that could be applied to 2D or 3D. So then we have to consider: do we want to interpret the world around us and then put it into a 2D plane as we are in the simulation, or do we want to actually have the robot in 3D detect objects and understand what it's seeing in 3D? Does that kind of help, or is there?
Yeah, that's good.
Yeah. So that's currently the stage of it. And then that's on top of all of that. There's different types of algorithms you can use to train in it. So like I said, we're using PPO. It's pretty basic and easy. It's just building weights on top of weights. So even if you have a negative behavior, it'll just build positive behavior on top of it to, I guess, mask it. There's alternatives like Q-learning, which there's tons of algorithms for Q-learning where it's you actually modify your old weights and get so that it's a more efficient model, I guess. It's a smaller model, but it takes a lot longer to train to get something that runs that efficiently. And it usually results in a bigger model after you've trained it. But regardless, there's a lot of different avenues.
So what specifically are you trying to get the AI model to be able to decide? Is it trying to do path planning? Is it trying to?
It's gonna do. Each stage of the competition is we're gonna probably have a different model. Well, we don't know yet. We haven't done enough testing. It's either gonna be one model or the same model, but it's going to be if we're in stage 1, we need to first orient ourselves. So we could have an AI just for orienting ourselves within the starting zone. Now that sounds silly because that's such a simple task, but you have to think about the context of each AI. You might want to separate them. So maybe we have something that aligns the robot, then something that allows the robot to navigate and sort of explore around, grab dirt, and then we'll have another one that navigates to the zone where it has to deposit. We'd hope that from training it with enough experience that it would sort of instinctually know what the best direction and path is to take, just from its trial and error. So we're training it from coordinate and rotational data. So if it goes and picks up dirt in the top left corner, instinctually, just from its training, it'll know that it needs to head to the bottom right direction. So then it'll find the best path based off of how it's navigating around objects, and that's just part of the training. There's different things we could do. We could integrate. We were talking about integrating pathfinding, as in having it try to search around first and then take the best optimal path, or tracking the coordinates it does follow, and then trying to trace back on its way back to the digging zone. So there's a lot of factors, and we can. Most of them would probably work. It's just which one is the best.
So what's going to be your decision-making process for deciding what's implemented as AI and what's used more on a conventional algorithm for? Path planning has plenty of different algorithms out there that you could use.
Mm-hmm.
What's going to be your decision-making on a basis-by-basis thing to decide what you're going to use for each individual task?
I guess it depends on the data that we think we can accurately provide the AI, and also what's easier to just have, what we want to control. We might want to control the path it takes. We may want it to take a longer path if we think it's safer, or we might want it like we might want to have options, you know, but for paths. We might not always want it to just take what seems like it's the easiest for it, because I mean, for us as people who are still observing and controlling the robot, we still want to have some sort of control. We don't want it to just I mean, we do want to hands off it, but it needs to still be reliably controllable. So, again, we're still figuring that out for ourselves. I mean, there's a lot of things to consider. I mean, I doubt that, from what I've been looking at, I doubt that we'd be able to just feed the robot or the machine learning a bunch of 3D data and have it interpret that environment. It's going to be a lot quicker for us to develop a 2D environment, and we just interpret the 3D data ourselves and then feed it that in 2D. Just from a practical standpoint, it's because I mean, you know, there's companies that spend all their time doing the 3D stuff, and we're just a design team that has a few months. So, yeah, interpreting 3D data in a 2D plane is probably going to be the quickest method to get the machine learning working. But yeah, we have to figure it out as we go, I guess. We're slowly figuring it out, but it's a little bit of trial and error.
I have a question.
Yeah.
How efficient are heat sinks on the moon?
Not very. So I haven't taken heat transfer yet, which covers more of that, but there are basically 3 kinds of heat transfer, and there's only one of them that you can use on the moon, which is radiation, I think.
Radiation, yeah. Conduction you can use a little bit, but it's rough because the soil is heat insulative. That said, for our sakes, the amount of heat we're generating versus the size of the robot for the time we're going to run, it's not as big of an issue as long as we're dissipating into the robot. The whole robot's not going to get above, you know, I don't actually have the numbers for it, but it's not going to get, like, we haven't had issues with touching the robot after a run, anything like that. We don't generate enough heat. We spread off across the entirety of the robot.
Even
to be
when
an
it's
issue.
concentrated.
If we were
in
talking
layers.
about running for several months on end, that's when we have to worry more about how we're going to get the heat off of the robot.
I genuinely didn't know, so that's why I'm asking
Yeah.
the question, but.
The thermal syncing for like the motor controllers, though, the FETs really don't need a ton of I guess like mass. They just need something touching them to make sure that they don't like overheat. As long as there's some sort of something conductive touching them, then usually they'll be fine.
I think I would be in favor of the aluminum box because I've used those plastic ones in the past, and they break kind of easy, especially with that plastic lid and the hinges. It's all plastic, and you'd have to be really careful. But it gives you a good heat sink for everything that's going to be in the box, as long as the box is totally, or all your electronics are totally isolated from the box.
Mhm.
And you can do that even with the FETs, with those little Mylar pads.
Mhm.
They
Right.
get it closed, but
Yeah.
they don't touch.
That's not a bad idea.
I would go for the aluminum. I'm looking at a box about the same size for a project right now, and actually I looked at the one that you had up there,
Go back to
but I didn't like those metal feet that come off at the end, so.
You did or did not like those?
I liked them, but I didn't like the little feet that come off at the end. The mounting bar, I guess you'd call it. See how that box has a,
Yeah. So when I was looking at enclosures and when I've been looking for enclosures, most of the ones that I found aren't, you know, designed for something like this. They're meant to be mounted on a wall or on a panel or freestanding on the floor. And that's kind of an issue in just sourcing them, right? Like all of your standardized components, like the NEMA standard that exists for enclosures as well, and really any big like wholesale electrical enclosure site, they're all designed to be used on a wall, and it's probably going to end up being we have to modify it ourselves for what we want, because a custom enclosure would cost us a ton of money.
there are some ones that are thinner aluminum, and they don't have a door, they have more of a panel that you just screw on. It's got, you know,
Right.
it's got the gasket in there and everything. I know doors are a whole lot more convenient to work with, but, you know, you could save some weight there.
Yeah. One of the things that we also consider is ease of access, right? Like a lot of the times you're working very quickly to be able to get in there and change something, either because it's something you've discovered. Anybody who went to comp any of the 2 years knows there's always something that you figure out last minute. You know, anything that can go wrong will. So having the ability to be able to quickly open it, change things, and reclose it back up is something that we kind of look for, and that's why I personally am looking for one with a hinge, rather than having 4 screws, just to kind of reduce that time to make it easier for us when, you know, stress is very high and time is of the essence to be able to change it quickly.
That's a very good point. If I could hog the floor for just one more minute, I saw on one of the first slides of the motors that there was a AC rating on it.
Are you talking about mechanical sides?
Where was it?
When
Was-
they spent out what the motors were gonna be.
Did we talk about them?
It was early
Yeah.
on.
It was mechanical.
We might have.
Mechanical section.
It was one of the first things I wrote down. I said, oh, AC motors, you can't use AC motors.
Not there.
There it is.
Oh, yeah.
Features 2 NEMA brushless AC motors.
Yeah, so the text on this slide is stuff that we wrote last year that we honestly forgot to change this year.
Okay, just as long as you know you can get AC motors.
No, what it should say there is 6 times brushless DC NEMA 23 motors, which I said when we were presenting this slide just because I know it off the top of my
I
head.
could just say it, but when I saw it in the writing, I thought, I'm just gonna ask.
Yeah, like it says like chain system where we're planning on linking the wheels with chains, and we're not planning on doing that. That was our design from last year, and we overlooked that. We apologize.
So the wheels are, I assume they're not gonna be independently.
No, so they are mounted directly onto the motors, and the motors are mounted directly to the frame. So they're rigid compared to the frame and everything else.
Mounted directly onto the motor gearbox combo.
Correct.
Are you gonna use the same ones used last year?
No, last year we used these big chunky NEMA 34s.
Those were heavy.
Those were very heavy, and 6 of those, just the power budget alone, is way too much for us to currently use.
So, my concern would be using torque when you hit a small hill that would pull the center wheel off the ground, I should say off the moon.
Mhm. So that's
You could possibly have 3 more motors on one side, giving you all the torque that you put into it, and ones on the other side would lose a little bit of traction. If
Yeah.
you had one off the ground.
So our main reason for choosing 6 wheels instead of 4 is that the teams that have used 4 wheels in the past have had an issue with digging themselves into holes, where basically they've been digging, and because they only have 4 wheels on flat ground, they lose traction and they start digging pits under each wheel. And it's much harder to do that with 6 wheels instead. So even if we just made the center wheel like a caster wheel or a free rolling wheel, it would still help with digging ourselves into a hole. So that's mainly why we're doing this. It's also because of traction, of course, but that's just that we don't get stuck like we've seen so many other teams do.
So the center wheel will prevent your front wheels and your rear wheels from going down.
Correct.
digging a hole.
Yeah. And even if like all 6 of them do, now you have traction over a much larger surface area just because it's sunken into the regolith.
You'd almost get more traction if it's sunk a little.
Yeah.
So I think I get what you're saying too about how you may have like a torque imbalance on one side versus the other. One of the things about the controllers that we've designed that Adam's put a lot of work into designing is that they do have feedback, right? So a lot of that is like current sensing. So you know, to get to this RPM, it's using this much current, right? And you know, your torque is derived from your current. So by seeing that you're not having any real torque applied to that middle wheel, it can communicate back and forth to your kind of main controller. So it could say, okay, well, you know, we're
slipping.
Yeah, we're slipping on this side, or this wheel's not actually doing anything. And ideally, it'd be able to account for that and say, okay, well,
Slow the motor down or.
yeah, slow the motor down, combined with the feedback that we'd use from something like April tags to know where we are in our orientation. It would be able to update in real time, you know, the RPM or the torque applied to each motor and be able to correct for that.
Yeah, well, maybe a better word I should use is traction. But torque kind of does equal traction in a sense. The more traction you have, the higher torque you're gonna have, the more current you're gonna pull.
Anyone else?
I
Patrick?
saw Pat's in first.
How will one digging system be chosen over the other? What's the criteria for that?
So we have a few different ways we're going to do that. The least trustworthy is just vibes. which we're not gonna put all of our eggs into that, but, oh, can I?
Look at that screen.
So this is not our boulder design. That's also something left from last year. This is our front loader design. So imagine it's just got a bucket on the front that you can raise and lower on arms, and then it's got basically a wrist actuator. So that one is going to be able to dig just like we've seen, Akron do, just like we've seen Utah do, Iowa do. It's a very proven design, just one that we haven't used so far. Another one is the bucket chain, which we've also seen other teams use a lot. So basically, we're going to have multiple decision matrices, and we're going to weigh, complexity, weight, cost, how much it can dig, theoretically, since we're only going to build one of these. And once we've finished all of that, we're going to choose one.
Speaking of different mechanical designs for excavation, have you guys done any estimates on how much regolith you can get per run? I know software was talking about wanting to minimize tracks back and forth with power usage.
Yes. So just basing it purely off of, and this isn't like a time-based thing since you said per run. So the difference in time for the bucket chain and the front loader is going to be massive. Bucket chain is going to take probably a minute per run. That's just because it has to go very slow and it has to fill that entire rear bucket first before it can dump it. Otherwise, it's just being super inefficient. And so the front loader is probably only going to take 30 seconds maximum per run because all it needs to do is lower the bucket, move forward, scoop it up, and drive off. So.
Okay, what's the difference in amount of regolith moved in per?
So right now, the bucket that we have spec'd out for the front loader is about 4 liters. And the one that we have for the bucket chain is about 6. So, you can kind of weigh that against each other. 30 seconds per run with 4 liters versus a minute per run with 6. Right now, it's looking like the front loader is going to be slightly faster. So we're leaning towards that.
And are you confident that you can fill up the entire excavator bucket every run without slowing down?
No.
So is that a concern when it comes to picking your excavation?
Well, it's not really a concern because it affects both of them almost equally.
Well, the bucket chain, if I'm understanding from your design there, will drop the regolith into that bucket or conveyor belt, however you decide to implement it, right? So it's dropping down on top where the excavator has to worry about like the efficiency of how much it's getting as it moves changes based on how much is in there.
Yeah, so it's not exactly the same because we're dumping the regolith out of the bucket chain design out of a separate system than the collection. But driving forwards with the bucket chain system, you're still going to get 30% of the buckets unfilled or whatever. And that basically translates to the other system being, 30% less filled. So it kind of balances out.
I think what he's saying specifically is that while the individual buckets may not be 100% full, you can still fill up your collection bucket to 100% regardless of each of the individual.
You can, but say each is 30% less efficient, it's going to make them 30% less efficient equally.
Well,
it's not going to be weighted one or the other.
Yes, for specifically the digging portion, but not the driving over to the burn zone and dumping. That's my question there.
Oh, keeping it filled while driving?
How that was a concern for power usage because more travel is more power used.
Do you mean you're concerned about us keeping it full while we're driving?
Yeah. So I think what he's saying is that while each of those individual buckets may only get 30% full, maybe that means you sit there and you dig another meter and it takes you an extra minute, right?
Yeah.
Whereas with the bucket, the front loader, if you only get it to 30%, you then need to take the time to drive all the way back, dump it, and then go back and try again, as opposed to maybe that takes a lot more energy than just digging for another 30 seconds to a minute with the bucket chain, I think is what he's getting at.
Is that what you're getting at?
That is the only exact.
Okay, so we 30% was honestly just a number that I pulled out of my ass. It's probably going to be very hard to get only 30% of that bucket filled, and that's just because the angle of repose of lunar simulant is so high. So once it's in the bucket, it's not really going to come out.
Yeah, once it's in the bucket, the problem is getting it into the bucket and having the torque to push through the regolith, which compacts like concrete as we found last year, without bucking up on the
Rear wheels. Yeah.
which would then lower our traction before
Yeah, so there's a few things that you can do to mitigate that. Number one is making a really short and tall bucket so that it only has to push in a certain amount into the regolith, and then it can tip the bucket back. And another one would be to vibrate the bucket to make sure that it gets full. We saw a few teams do that last year. But we're looking at different ways that we can to make sure that the bucket is filled to at least 75% capacity during every run. Did that answer your question?
I think so, yeah.
Okay.
Seems like you guys are asking or answering the right questions. One more question for the mechanical team.
Yeah.
So software had mentioned again that they want several cameras on the robot. Is there plans for how to mount those in your design?
It isn't shown here because we haven't done the CAD on it yet, but we've done hand sketches. So basically,
CDR.
yeah, that's coming in the CDR.
Okay, but there is plans. in
There
regards
is. We're
to-
going to do some sort of a tripod mast, basically, that's going to go up between the two arms on the front loader or mounted somewhere on here. That's another design consideration for the bucket chain, is because there's not really a great place to mount anything else. But we're going to have places to mount all those cameras and the depth camera and all the sensors that they need. It's going to be a lot easier to do on the front loader.
So yeah, you said there was a tripod, right? Is the plan as of right now?
Tri or quad pod mast, yeah.
How are you planning on dealing with vibrations there? As you know, extending up the camera is going to increase the effect of vibrations.
So the more legs you have, the less vibration you're going to get, just because it's going to be stiffer. And carbon fiber as like a material is already incredibly stiff, so we don't anticipate like high vibrations like you would get on like thin metal like spokes or something.
Yeah, but the stiffness actually does less to attenuate the vibrations. Is that not a concern? Do you have any plans for like using rubber padding or stuff like that?
So rubber padding, our concern to do rubber padding or like any sort of compliant mechanism is that over time their like position zero could shift, and it could get out of alignment with where we think the camera is on the robot, so the data could get like kind of jumbled up. So we think that the stiffer it is, like the easier it is for it to stay at the exact same position on the robot, the better, even if you do have to consider a little bit of vibration noise.
I guess that would be more of a question for software. Is that a major effect for any of your designs, vibrations versus a slight shift in?
I think taking vibrations is going to be significantly easier than dealing with any sort of shift in the camera's perspective. If you have any sort of pitch or roll on the camera, it's gonna. I mean, it's such a little amount of degree of freedom in either direction is going to screw up triangulation. So, being stiffer, even if there's vibration, is in being sure that we're at least within like being sure that we know where the camera is for sure is going to be more beneficial for our localization. And it won't be moving fast enough or anything. I don't think that we'll experience much vibration. So we want to probably plan more around it not vibrating than to
Especially at the
dampen it.
lengths of material that we're going to need for the mast. Vibration at all isn't really an issue. You get more of that when you're getting to the materials. Like, imagine you're holding out a stick and you start wiggling it. You're going to get a sine wave, right? The carbon fiber has such a long, I forget what it's called, but yeah, it's resonant frequency is so short that you're basically only getting a tiny way of the way along that sine wave, so the vibrations are really, really short. So they don't really have time to build up at all. You're not going to get any resonance, is what I'm trying to say.
Not to hog all the questions.
Going off the conversation, couldn't you guys build like a test mount to test this idea, just to make sure that sound before you even pick up the robot, just to make sure that it's not going to see any negative vibrations?
Do you mean vibrations from driving over the surface or vibrations from like operating?
Oh,
So over the surface, like the entire robot's going to be getting vibrated, right? There's no way, unless we use like a gyroscope to hold that mount there at that specific angle and position, there's no way for it to stay at the exact same height above the surface at the exact same time, like continuously. It is going to be getting shaken around as we drive over uneven terrain. There's basically nothing we can do to stop that. Just, we can attach it anywhere on the robot, even if it's not on a tripod mast. It's still going to be getting shaken at that same amount. except I guess it will be lower down on the lever arm, so we can try to mitigate that by reducing the height of the mast.
In terms of testing, like you mentioned, are you talking about building something not dissimilar to how they test like scale models of buildings where you shape the base and see if there's any?
Kind of. It's like building like a carbon, like an element structure. Yeah, I guess what you're saying.
Having some kind of mount where you can vibrate the base at a specific frequency, maybe sweep it and see.
And see how much the carbon fiber actually vibrates when shock goes applied.
Yeah, that's definitely something we could look into, and if we're concerned that vibrations may become an issue, that's something we may end up doing. So, I appreciate the question.
Based upon some of the FRC stuff that I've seen, as soon as the camera captures the April tag, it follows it. So if it's vibrating around, it'll follow it.
That's something too, where if it does become an issue, that's like where we look into our concept of operations of like, okay, so we know where we are given the April tags, and we know what we see immediately in our view, right? And as inefficient as it may seem, we can always stop if vibrations do become an issue. Just take a short pause while we're moving to reorient ourselves, make sure everything's all good, and continue moving again. Like there's methods in not just how we design the robot, but also how we operate it to mitigate things like that.
David here brought up a good point that our capturing is not going to be at a high enough sample rate that you might not even see vibrations anyways, as we're probably only going to be operating at like 5 to 10 FPS per second.
It's gonna capture the values so quickly.
Yeah, I mean, it's unlikely that it'll be as big of an issue as if we were doing it at like 60 FPS or something higher. Yeah, and again, we can do some sort of like gimbal stabilization if we want to, which actually might be easier to mitigate, the robot moving through craters, or not through craters, but through divots in the ground. So there's also some digital stabilization I guess we could do, or look into at least.
Do you have any like personal experience in dealing with the vibrations and stuff? Anything you might recommend we do differently than what we've talked about already?
I keep sitting here thinking that, wow, there's almost no gravity on the moon.
Right, and well,
Suspended and then.
Yeah, you've brought up a couple good points on, how the design would apply to the moon, and while I know NASA focuses on being as realistic as possible, there are a couple things where you really just can't, like, you have to realize that we're not operating on the moon as much as we'd like to, right? Like you brought up the heat sink, and realistically you'd have to design a way to radiate that heat, and that would add so much weight, and it's kind of at the point that while we'd like to simulate working on the moon, at the end of the day we're still not, right? So we have to account for Earth gravity when you talk about traction. You have to talk about how it does have the ability to conduct heat just into the air, dissipate heat into the air, which wouldn't happen on the moon. And you have to deal with the kinds of vibrations you'd see here on Earth. And as much as, again, like I said, we design around lunar operation, there are a couple things that you just can't escape being here on Earth still. So.
Yeah. If I could just skip back a little bit to the designing your own motor controllers.
Mm-hmm.
That's an interesting choice. There's like millions of us on the market.
Well, and we talked about this, we did. And this being a design competition, we also believe that there is some benefit in just gaining the experience of doing it yourself. It's, like you said, there's a bunch of them out on the market, which also means there's a bunch of references for how you can design these things. And
we can make them more compact from what we've seen than traditional off-the-shelf controllers. There's a bunch of other stuff, like we said, like our old controllers, they already have a defined mode of operation. We haven't actually played with anything like RS-422 controlled drivers or anything, but with this, exploring CAN, and then also having motor controllers that have telemetry such as like current per phase and stuff, we think that using a custom controller and being able to streamline our data in a way that makes sense across all the devices, like our actuators can have the same type of data that the motor drivers also have. It's beneficial, for tracking power being able to like cross compare, like when we have our external power meter versus our internal one, is it lining up, and it makes it a little bit more easier to integrate the systems, even the subsystems, even if it's a bigger design challenge now, I guess.
It also allows us to kind of pick our own like fault conditions, right? Like that's just another example. We can pick which data we care about that the robot needs to receive in order to or the controller needs to receive in order to function, and which data the microcontroller actually cares about getting back from these controllers. We can the driver that we have picked, we can kind of define certain characteristics, like its acceleration characteristics, its current ramp up characteristics.
We can change the delay between FETs being triggered, so you can change there's braking built in, and you can set all these parameters, it's a little bit more dynamic than we're used to. Half the issue we ran into before was we would run into all these faults, and all you get is a blinking light, on the motor controller, and there's no data line.
Right now.
Yeah, there's no data line to understand what that fault actually means, and if we build it from the ground up ourselves, we at least know. We can create methods of indication, and we at least know what the faults mean.
So this one, is this your layout?
Yeah, this is our layout currently.
How many layers is the board?
This is a 4-layer board.
4-layer board?
Yeah, so there's 2 signal layers, top and bottom. There's the second layer is a ground plane, and then the third layer is a power plane. Split power plane, I should say.
And how are you planning on getting it? Are you going to build it yourselves?
We might build the first versions ourselves, but once we have
We might populate the first version.
the first versions ourselves and bake them or something. But
yes.
When we go to order like 12 or something, we'll probably have some sort of PCB production house do those.
In terms of ordering them, like the boards, the physical boards themselves, just the PCBs, not even the components. There are plenty of affordable prototyping companies out there. JLC and PCBWay are the 2 that come to mind. If you were doing this for an actual like space setting, you'd need to go through a lot more, advanced manufacturing techniques. But we can get away with using something that's affordable to us as a college design team. I think you can get a handful, like 5 prototype PCBs from JLC or PCBWay.
Including shipping for like $4.
Yeah,
That's
like $4. I think the most I've gotten when I was paying for some expedited shipping was like $40, and that's most of that was shipping. So for 10 to 12 boards,
the board cost won't be the expensive part. It'll probably be the components themselves.
It'll be the components and it'll be the shipping, and the shipping stays relatively flat over quantity. So I would say it's not an unreasonable cost.
Who is a good surface mount solderer?
Sorry, a good what?
Good surface mount solder.
Oh, personally, I have soldered probably over 10,000 components by hand.
Using what?
My hands.
Yeah, but like what?
Wait, sorry.
An iron?
So an iron and just an iron and a heat gun. Well, so I flowed them using like an actual like heat lamp, but placing the components by hand, I have experience with.
So you put it on a preheater,
Mm-hmm.
and then used air, hot air to.
Yeah, to flow.
Use a real soldering hot air or a heat gun.
No, yeah, a real soldering station with hot air.
Not to mention also do have a parametric solder as well.
Also,
We also have multiple sources of such as Akshat here who have access to production houses. So we have some internal resources.
We have sponsors.
That's the most expensive part about getting it, is having it populated.
Yeah. Oh yeah. Doing some sort of SMT taking place is going to be very expensive. I mean, I know from personal experience that just a board with only 30 different components can be about $25 per board just for something that's like 50 by 50 millimeters. This is a little bit more intense than that. I think it's like 50 different components, so it's going to be a little bit more than that. I mean, the thing is, we only need 12 boards, and if we have, honestly, if we built them by hand, it's not completely unreasonable if we assembly lined it, but
Yeah.
that is a good consideration.
It's one of those things where we can use it as a learning experience for our team members, especially in the prototype phase, where you're not really crunched for time as much, and you can deal with a handful of clearly we soldered something wrong, so let's trace down where that happened. As much as I take the competition seriously, I am a firm believer in we're here to make our team members better. So if they haven't had that experience, then I'm happy to give it to them. But when it comes down to okay, we need our 12 good boards that we're gonna use for competition and as our replacements, I am not opposed to having them populated by a professional board house. I think Adam said the component cost,
It's around
it's like $45,
$45.
$46, and then having access to sponsors with board houses, getting them populated for free or next to nothing is
I doubt they're gonna put them on the line, they'll probably just have one of their technicians
Yeah.
handle it.
yeah, that's
Which is ultimately what we could do. But
yes, and so like you said, there is the trade-off of that's probably a more reliable way to do it, to have somebody who does it as their full-time job handle it. Or we could do it ourselves. It's just one of those things where we're gonna have to cross that bridge when it comes time to actually order them.
Well, you could also, when you design it, think of that.
Right.
And you could use through-hole parts to make it easier,
Mhm.
but, you know, I don't think you're gonna get a lot of those chips in through-hole parts
Yeah.
anymore.
Right.
Or,
well, the problem is if we use through hole, then we design around being able to do pick and place if we decide that or if we find somewhere that will do it for a good cost. So it's we can make a different design. Through hole would be a great idea if we want to go with the hand placing route. But yeah, again, that's just another consideration.
But then you trade off space, right? Like you
Yeah.
can't these boards, being the form factor that they're in, probably wouldn't meet that anywhere near that form factor if all those resistors, capacitors. I mean, barring the two massive ones.
Most of them were actually selected with the intention of being able to be hand placed. I think the smallest part is an 0805. So most of them you can use tweezers and a little bit of precision placing to get on the board. It wouldn't.
you also might wanna consider using some relief around some of the bigger pins that are gonna have to
Yeah.
solder, and if they're going on a heavy copper layer.
Yeah, so I should have put like a transparent layer image, but under the fence is solid copper, and then there's thermal relief vias underneath each FET. I think each one has 24 vias, I believe. So all of the heat is being sunk into a copper plane underneath this, and then all the way through the ground layer, and then also the bottom signal layer. So there's a lot of thermal mass.
Well, that's your enemy when you're trying to solder.
Yeah. Oh yeah. It's yeah. Yeah. Well, we'd have to heat the entire board very evenly to get those to flow. I don't have experience flowing a part this big yet, so it'll be a learning experience if we do that.
Well, just make the concept that you have to heat up as small as you can.
Okay.
I mean, as small as reasonably you can, but I guess my overall point is just be careful.
Yeah. No, that's a good thought.
Just be careful.
Yeah, you asked why we would do this, and I think the idea kind of came from me selfishly being like, it would be so nice if we had a motor controller that worked over like I2C and had this register for this and this and that. And then I was like, well, we can just make one. So it's kind of going to make the software, I mean, apart from the fact that we'd have to write the firmware, it'll make the actual software integration really seamless.
Yes, I agree. I would love to make an H-bridge motor controller for myself, but I don't need one.
Yeah.
But I'm assuming you're doing H-bridge, I can't see from up there.
Yeah, it's an H-bridge.
It's a 3-phase motor, so just positive and negative for each phase is
Yeah, but if you want them to run in reverse, you're gonna have to switch it over.
right.
I think the driver handles all of the
Oh, the driver should handle it.
Yeah, it handles both directions.
As long as you're not writing that software.
No, yeah, that's built into the chip itself.
Because that's very tricky,
Yeah.
getting just the right delay between.
Yeah, and so there's registers, in the chip that you can set for the delay between the FETs triggering and stuff. So you could change the registers in a way that would make it dangerous. But as long as we stick with like what's recommended for driving the FETs, then we should be fine.
Yes, it blows up very.
Yeah.
As well. I'm dealing with that right now.
Yeah.
They just blow up.
Yeah.
No, I
Luckily, these
don't
are
know how-
like actually marketed as
that I'm
Texas
good, 'cause
Instruments like
unless I
smart
can-
BLDC motor
can't,
drivers for like high power applications. So they have all those built in. We can change parameters like that. Yeah.
Yeah. All right. Well, it's getting pretty late.
I have one more question.
Last
All right, last question.
I got 12 more, wait a minute.
Is there a plan to isolate the 5-volt system from the 24-volt system?
The 5-volt systems are all powered. So like the 5-volt system. The 5-volt bus is coming from all of the motor controllers, and they all have 3 amp 5-volt power. So they're all. So to answer your question, no.
Okay, so in terms of a separate supply for like your Raspberry Pi, your Jetson, your Mac Mini, whatever you want to call it, whatever we end up using.
Oh, I like that you're thinking about it.
So that's probably going to come from a separate battery, one that doesn't have to be shut off during the e-stop. And the only like physical connection that they have to the rest of the system would be the CAN bus. And there are CAN isolators for sale, just off the shelf, that we could use.
I have to check. The bucks we have might be like.
I'm talking about like.
I know.
So yeah.
But we have methods of powering things. If we need to do isolated, we can look.
Yeah, like even the 5-volt buses on the motor controllers themselves can potentially be isolated.
Yeah.
That's something diving into the drivers. That's a great question. I would say that my like default what's the word I'm thinking of? I'm kind of leaning towards just isolating the CAN bus, the node that goes to your kind of brain of the robot, from everything else, where you handle your motor controllers and things like that. I would say that's the easiest way to just really ensure.
Plane you have in the middle.
You do it in the ground
Some
plate.
gears in there and some zero ohm resistors. to
Right.
connect them. And if for whatever reason, if you get too much noise or feedback,
Mhm.
you can pull those resistors off and separate.
Right.
Okay, well, thank you everyone for coming. We really do appreciate it. It is getting late, and it's getting time to cut it off. So again, thank you so much. If you filled out one of these feedback forms, please give it to me or one of our other lovely officers. But other than that, don't you do it. Other than that, thank you for coming. If you have any other questions, feel free to pull us aside.
Cool.
All right.
You